Hi everyone. Today we're going to discuss some topics of ray optics for grade 12 CBSE. In grade 12, the last part of ray optics is nothing but optical instruments. So some of our students, they are struggling in drawing ray diagrams of optical instruments. It's basically because, instead of considering it as a single diagram, you should learn the sequence in which the ray diagram is being drawn. So anyway, we will go ahead with the contents of ray optics. I hope all of you have your pen and book, pencil, scale with you. If it is not there, you go and get it. We will study how to draw ray diagrams and some of the derivations related to this physics. For grade 12 CBSE, ray optics, of which optical instruments. Now, the optical instruments are broadly classified into this. You can have a look at this whiteboard. We can classify optical instruments into two. One is microscope, and second one is telescope. The microscope we can further divide into two, which are the two types of microscope we learn: simple microscope and compound microscope. Even telescope also, we have two types, which is refracting type of telescope, and then we have reflecting type of telescope. The refracting type of telescope, it's basically, we are made up of lenses, right? That's of two types again. That is astronomical telescopes, or those are used for astronomical observations, and the one which we use for terrestrial observations, okay, on surface of the Earth. So two types of refracting. Now, even reflecting type also, we can say it is classified into two, namely Newtonian type of telescopes, and the other one is Cassegrain type of telescope. So if you look at the picture, you'll be able to make out in what all ways the optical instruments are divided into. Okay, as per the CBSE portion, now we have to learn simple microscope, compound microscope, and the astronomical refracting type of telescopes in detail, including ray diagrams and some of the derivations. And terrestrial telescope, we don't need to learn as per the syllabus. Okay, further, the Newtonian and Cassegrain telescopes, you may learn the how to draw the ray diagram. Okay, that is the case with as far as the content is concerned. So I hope it is clear. So you can look at how the optical instruments are being classified. The next thing is, I'll just show you a few such devices. Like optical instruments, from the diagram you can make out that this is nothing but, what we commonly call this as, we call it as a magnifying glass. No? This is a magnifying glass. Okay, but this is what is here named as simple microscope. And these two are the two different forms of a compound microscope that we'll study. So simple microscope, compound microscope. And next, I'll show you how the astronomical refracting type telescope. This is a refracting type telescope for astronomical observations. Okay. Then another one we have is this one. This is the terrestrial telescope. Okay. This one is what we use for terrestrial observations. This is what is otherwise referred to as, binoculars. You're familiar with that. Okay. They're nothing but terrestrial telescopes, generally speaking. Okay. Then another device, I'll show you another optical instrument is the, in the reflecting type telescope itself, we have two types. This is the conventional, what we call as Newtonian type of telescope. Okay. Okay, have a look at that. And another one is, this one. This is the a form of Cassegrain type of telescope. Okay, I showed you all the different types of optical instruments which we have to study, or except binocular or except terrestrial telescope, everything we have to study as per the syllabus. Okay, all of you are ready? just give an introduction, the overall picture about what is going to be there in optical instruments, the classification, and the examples of the different types of optical instruments I just showed you as well. I hope all of you are ready. Okay, we go ahead with ray diagrams and the derivations. Okay, I'll just take the whiteboard. Okay, so we will begin with simple microscope. Okay, you write the title, simple microscope. All right, so in this, in a simple microscope, as I showed you, it's nothing but a magnifying glass. So magnifying glass it's nothing but a convex lens. So convex lens, where it will form or when it will form a virtual image. It will form virtual image, just to see, it will form a virtual image if the object is kept between focus and optic center. So let's assume an object is kept between focus and optic center. See, this is the focus, this is the optic center. Okay, focus to F. So what you should do is, when the object is between focus and optic center, what kind of image you get? When you've studied that, you will get a virtual enlarged image on the same side as that of the object. This is the basic, what you can say, principle of the simple microscope. If the question is, what's the principle of simple microscope? You can say, when an object is kept between focus and optic center, an enlarged virtual image is formed on the same side as that of the object. You just consider one light ray parallel to the principal axis. It will definitely go through the focus. Okay. Another light ray you take through the optic center. It will continue going ahead. So you can see these rays can be extended. If you are looking from this side, okay, looking from this side, and these rays can be extended. So just draw this one straight. Okay, use a scale and draw it or extend it backwards. This also use a scale and extend it backwards. Okay. So when you extend these two lines backwards, you will see that they will meet. Okay. Let me say they'll meet here. So just need to draw. They don't need to make them meet. They will meet. So they will meet somewhere. There is no specific point like that. It should only be. You should only consider that it should be on the same side as that of the object. It's no specific position like between F and 2F or nothing. This is the virtual enlarged image formed by the convex lens when the object is between focus and optic center. Look, AB is the object, A dash, B dash is the image. AB is the object, A dash, B dash is the image. If you got it? Yes. Next thing is, we have a term to define and to derive the expression for, that is called magnifying power. Okay. So let us define and derive expression for magnifying power. Magnifying power of a simple microscope is, generally speaking, for a microscope, the magnifying power is defined by the ratio of two angles, theta I and theta O. Theta I is, which is the image here, A dash, B dash is the image. Okay, A dash, B dash, this is the image. So that image is making an angle with I or with a lens. Okay, that angle, that is A dash, B dash makes an angle with the lens. This is theta I. What about theta O? You may think that theta O is that angle itself. But for defining theta O, we should consider the object separately. Just look at the object. This AB is the object. Okay, same object I'm drawing here. So all of you remember this point. When you define theta O, we don't need to consider any lens or anything. We just consider the object AB, which is kept at a distance, what we call as the least distance for distinct vision. That's otherwise we are keeping the object at the near point. Near point. Okay, now for normal person, distant if that's represented by the letter D, capital D. Okay, so now you look from this side. This is your eye. Okay, then how much angle that will subtend with the object? That is how much angle the object subtends with your eye. if the object is at the near point, or if the object is at the least distance for distinction. This is theta O. Is it clear? Theta O is the angle subtended by the object with the eye when the object is at the near point. Clear? So, but as one thing we should understand here is, in any optical instrument, say the microscope or telescope, we can consider the image position at two extremes. One possibility is, the image is formed as close as possible to your eye. What's that? That is the least distance for distinct vision. Okay, D. Second extreme is the infinity. So in each case, therefore, we have to consider, in each optical instrument, we have to consider two positions of the final image formation. So here we assume the first case is the final image is formed at D. The final image is formed at D. This is the first case. Second case will take final image to infinity. So that means here this distance to the image is also D. By the way, let us write the object image distances. So this is the object distance U. Object is at this point or at that distance, and V is the image distance. But in this particular case, the distance V is going to be taken as D itself. Okay. Therefore, you look at this diagram. This diagram we can incorporate into the ray diagram, main ray diagram. That means, here the final image is at infinity. So you just imagine the object is also drawn here. So A dash, E double dash. Okay, this is the object. That is, we imagine the object is kept at the same position where the image is formed. By the way, in this particular case, image is considered to be formed at the least distance for distinct vision. Therefore, we can assume like that. So then how much ever is the angle it subtends with the eye. This angle is theta O. In other words, we can also say that this diagram, this diagram you are putting it in the main ray diagram. Okay, then I'll wrap it up. That is, this diagram, it is possible because final image is formed at least distance for distinction. And one more thing to understand is, in trigonometry, we know that whenever angles are small, we approximate sine theta as theta, cos theta as approximately 1, and even tan theta also we can approximate it as theta. So here the converse also can be taken into account. Wherever the ratio of two angles came here, this can also be considered as the ratio of tan of the same angle, tan theta I by tan theta O. Fine. Now look at the diagram and let us replace tan theta I and tan theta O. Tan theta I, there again you see A dash B dash is the image that is forming an angle theta I with a lens. And by considering the similarity concept, you can also see that ABC also same angle theta I. So let us look at that small angle for this. That is something we should be clear about, which triangle you should take into account for tan theta I. Then I'm not considering the big triangle, I'm taking the smaller triangle for the sake of derivation of expression for magnifying power. By the way, magnifying power is nothing but similar to magnification only. As far as the single lens is concerned, is magnification. This is magnifying power. Okay, so we use for optical instruments. Okay, sometimes we use the term angular magnification as well. Okay, so instead of tan theta I, what I will write here according to the diagram, or if you look at the diagram and say AB by U divided by, instead of tan theta O, we can write A dash B double dash by V. But we know A dash B double dash means what? It is nothing but AB only, that is object. We assume the object is kept over there. So that means simply these two, that is AB and A dash B dash, you can cancel. Right? Those two we can cancel. So we get the magnifying power M is equal to V by U. Now we may naturally ask a question, okay, this equation we have already seen in the case of convex lens we have seen, or lenses we have seen the magnification, but we call that as magnification. Magnification is V by U. But in this context, even if it is optical instrument, we got the equation M is equal to V by U itself. That's because even if we call it as an optical instrument, this is nothing but a single lens, convex lens. That's why we got the same equation. But whenever you write an expression for the magnifying power of an optical instrument, it should be expressed in terms of the focal length. All right. So we can write, we can make use of the expression, that lens equation we can make use of. We can write, but 1 by f is equal to 1 by v minus 1 by u. And you just multiply the equation throughout by v, we get v by f is equal to 1 minus v by u. Okay, let me write it over here. Therefore, v by u is equal to what? 1 minus v by f. So from equation 1, we can rewrite it as capital M, that is magnifying power is equal to 1 minus v by f. But when you apply the sign convention here in this particular case, what does v represent? V is nothing but the least distance for distinction, that is d, capital D. And by sign convention, what you can say is incident ray is towards right, but you are taking the measurement towards left. So according to the sign convention, v is negative. So we should replace v with negative d. Therefore, the final expression for the magnifying power is 1 plus d by f. So I request all of you to memorize this equation. Okay, so this is the derivation of expression for magnifying power of a simple microscope. Is it clear? All right. Next is, I told you the two situations for a simple microscope. If the final image is at infinity, then what it will be? Final image at infinity. In this case, for again, I'm talking about simple microscope itself. Okay, consider the lens again. This is the lens, and we take the optic center, and here we have the principal axis. Okay, then the object. So this is the focus, optic center, 2f. Okay. Now, for final image to be at infinity, where should we keep the object? Okay. By the way, in the case of for final image to be at infinity, the focus, the object should be kept at the focus. You know that. So this is the object. The focus, we keep the object. Okay. One light ray parallel. The parallel ray after refraction will pass through the focus, and another ray through the optic center. It will go parallel. No image will be formed. Is that clear? So where is the image? Image is at infinity. That is, if you look from this position, you can see that, look where the image is. If you extend it further, it will not meet. It will not meet means image at infinity. Okay, to infinity. Okay, so that means the angle subtended by the image. This is the image line from the image. No, so this is the angle subtended by the image with the I. Sorry, image with I, not theta O, theta I. Okay, what about angle subtended by the object with I? That we define, that we have to define separately, as I said before. Okay, this angle, capital. That's the least distance for distinction. This is to define theta O. So again, if you look at the expression for magnifying power, we have the equation theta I by theta O, which is nothing but tan theta I by tan theta O. Okay, which is, look at the diagram. This is the focal length. So tan theta O, we can write as, say, let me write this as AB again. So it is AB by F whole pi. How about tan theta O? You look at the second diagram, another diagram. So AB by D. So the expression for magnifying power is D by F. So look at this derivation again. This also shows that in a simple microscope, once again, in a simple microscope, the principle is when an object is kept within focus and optic center, a virtual enlarged image is formed on the same side as that of the object. Correct? And the expression for magnifying power. If the final image is at the least distance for distant division, the expression for the magnifying power is 1 plus d by f. And if the final image is at infinity, it is just d by f. Okay, so I hope it is clear. So the next thing is the simple microscope is done. Okay, so the next topic is we have which one? The compound microscope. Okay, we'll discuss